to find the derivative of a function or a term that is in the form x to the n is n times x to the n minus 1. So we had gone through a couple of examples. You had also done the introduction that had more examples on it, and then using this in an example to find the equation of a tangent line. So we're just building off of this now to get to find the derivative of a polynomial, because this is really just the derivative of one term. So building to now a polynomial, and we'll then talk about the natural exponential function, the derivative of e to the x. So the constant multiple rule is next. And this is kind of like how constants worked with limits. So it makes sense, or should make sense, since the derivative is a limit. But it says if c is a constant and f is a differentiable function, then, again, they're using the Leibniz notation here. If you have the derivative of a constant times a function, that's the same as taking the derivative of the function and then just multiplying by the constant. So that's what it explains in words here. The derivative of a constant times a function is the constant times the derivative of the function. So if we look at example 4, if you are asked to find the derivative of 3x to the 4th, this would be the same as saying I want you to take 3 and then multiply it by the derivative of x to the 4th. Now, you're not going to write this out every time. I'm just really breaking it down to show you what you're doing. So I have 3 times, what is the derivative of x to the 4th? 4x cubed. So then this is 12x cubed is the derivative of 3x to the 4th. So basically, if there's already a coefficient of your term when you're using the power rule, when you bring the exponent down in front as a coefficient, you multiply by the coefficient that's already there. And then you still take 1 away from your exponent. So then the derivative with respect to x of negative x, what would that derivative be? Negative 1 times the derivative of x. What's the derivative of x? Just 1. So it would just be negative 1. Okay, and this you could also say negative x would be linear, because it's just in the first power. The slope of that linear function is negative 1. Would be another way to think of it. Any questions? If there's a constant already in front or a coefficient? Okay, so then getting now into actual polynomials, we have to then introduce the sum and difference rules. So these really are 2 different rules. I just combined them into one. So it's the same if you have a sum or a difference. So if you have 2 functions, f and g, and they're both differentiable, then the derivative of x plus g or x minus g, or I'm sorry, f plus g or f minus g, is equal to the derivative of f plus or minus the derivative of g. So you're basically just taking the derivative of each term and then still adding or subtracting them. So what I would like you to do is I'd like you to actually find the derivative of number 6, combining all of these rules. So you're finding the derivative of each separate term and just writing it as a polynomial. Okay, so work through example 6. I'll walk around and check that, but while you're working on that, if you finish, go ahead and start looking at example 7 as well. A lot of this you already have background knowledge from what we've already talked about in class. It's just now finding derivatives is easier. So use what you know already to work through 7 as well. Yes.
It was 4x to the 4th. Would it be 16x to the 4th?
Yes. Yes, just a second.
What's up? Alright, I'm gonna show you. Yes. Right? Is that right? Turns out this is like the shortcut isn't kind of fun. Because like you're like quick.
Better than you want. No. That's literally what I thought that we were doing. I was like,
What's the top one? Doesn't mind? What? Doesn't mind? Wait, but don't you have to do the second derivative? So,
oh no, wait,
Now you have 20 plus hours of life. That's what you call it all your off. You got paid for that. And then you have it out.
boom. Oh, after 2 seconds? Yeah.
so that's a day that you're gonna find out if you're
job, Stan.
He's wearing a shirt.
My sister.
Yeah, it's a little sweaty.
It's 14, right?
Yeah.
Every day.
It's, yeah. No,
Yes, it's all blue.
All right, I believe everyone had 6. And then remember too, if you're given y, you can notate the derivative as y prime if you're given it as y, or dy dx for the Leibniz notation. And then 7, as I said, the concept behind it, we've already talked about that if you're given position, so the equation of motion would be the position, that the acceleration is the second derivative. So first derivative would be 6t squared minus 10t plus 3. That's the velocity. And then acceleration is the derivative of that. So the acceleration function would be 12t minus 10. And then after 2 seconds, 14 centimeters per second squared would be the units for acceleration. Per second. So any questions to this point? Finding the derivative is much quicker now, but the concepts that we've covered are the same. You're still going to be working with position, velocity, acceleration a lot. All right, then example 8. Example 8 is more like a proof of sorts, not a proof that you will ever need to mimic on any quiz or test. But occasionally, as we go through rules for derivatives, I don't always like to just tell you, here's the rule, and you don't know where it comes from. So I like to relate it to some things you already know. So the proof, it's good so you understand why the derivative is what it is. But it says, compute the derivative of the exponential function f of x equals a to the x using the definition of a derivative. The definition of a derivative is the limit that we worked with the whole last unit, the second half of chapter 2. So we need this definition that f prime of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x all over h. And our f of x is a to the x. That's our function. So we have the limit as h approaches 0 of, so f of x plus h would be replacing the x, which is the exponent, with x plus h. So it would be a to the x plus h. And then minus f of x is just a to the x. And that's all over h. And then from here, we focus on rewriting some things. So first of all, what is a way that I could rewrite a to the x plus h using laws of exponents? Say that again. I can't just bring it down. Yeah, unless I was taking the log of it. Yes, I can. This is kind of working backwards from what you normally do. But if I have a power to an exponent that's being added together, I got this by taking a to the x and multiplying it by a to the h. So I'm kind of splitting it in the reverse of what we normally do. And then I still have minus a to the x. What? I think you did with a was 5 or something like that. Yeah, there was a problem very similar that you did practice of, yes. All right, so from here, anything you notice that we could do to keep simplifying this or rewriting it? Yeah, we can factor out a to the x. So limit as h approaches 0 of a to the x times, and then we'd have a to the h minus 1 all over h. And then from here, this is where, again, keep in mind this is more like a proof of where we're getting to. A to the x alone does not depend on h. So it does not depend on h. What that means, if we're taking the limit as h approaches 0, h is not affecting a to the x at all. So it's acting like a constant, meaning I can then write it in front of the limit. So because it doesn't depend on h, I can bring the a to the x in front. Because it's being multiplied, it's a factor of the rest. So I have a to the x multiplied by the limit as h approaches 0 of a to the h minus 1 all over h. And then from here, actually I might use a different color. This limit represents the derivative at a specific value. So again, this is all building with a proof. Not that I'm not just telling you to do this on your own. This is actually, if f of x is a to the x, this limit represents f prime of 0. And I'm going to show you why. The derivative at 0. So as a side note, if I gave you f of x equals a to the x and I asked you to find f prime of 0, that means going back up to this definition, the x's here would be zeros. So I would be finding the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. And then I'm just showing you how this is equal to that. So if I have f of 0 plus h, that is equal to a to the 0 plus h. And then minus f of 0 is a to the 0 all over h. And hopefully you can see then how that would equal this. 0 plus h is just h. A to the 0 is 1. So this limit represents the derivative at the value 0. So ultimately, this is saying our derivative f prime of x is equal to a to the x multiplied by f prime of 0. And f prime of 0, that is just a number. That's a constant. Now, it depends on what a is. That's why we can't continue. But this is a formula in general. For any function in the form a to the x, the derivative is equal to the function itself multiplied by its derivative at 0. Why this is important, we are actually going to have a more specific formula for the general form a to the x later. This is building us to find the derivative of e to the x, but why this is important, this says for any exponential function, the derivative is proportional to the original function because the derivative is equal to the function itself multiplied by a constant. So when we were even sketching derivatives, if you had an exponential curve, the derivative is also exponential, and this is why. It's just differing by a constant. So where this is leading, we expand on that formula later, but where this is leading for right now, actually I'm going to go back. If f prime of 0 was the number 1, the derivative would just be equal to the function, and that happens for a specific function. So we've already talked about why e to the x is so important in calculus. It's awesome. Of all possible choices for the base a in a to the x, the simplest differentiation formula occurs when f prime of 0 is 1, like I just said. By definition for the number e, this might be something you talked about in pre-calc, e is defined by this limit, that the limit as h approaches 0 of e to the h minus 1 over h equals 1. Hopefully you recognize by the formula we just wrote on the other side, this limit represents f prime of 0 when f of x is the function e to the x. So that's the limit we were just talking about as being f prime of 0, but specifically when the base is e. So this is saying if f prime of x is e to the x, the derivative at 0 is 1. So I have what the graphical meaning of that is. It means of all the possible exponential functions for a to the x, the function e to the x is the one whose tangent line at 0, 1 has a slope f prime of 0 that is exactly 1, and that means if we go back to, you're seeing how I wrote that, if we go back to saying f prime of x is equal to a to the x times f prime of 0, so if you have e to the x, f prime of x is going to equal e to the x times the derivative at 0 is 1, meaning the derivative is just itself. So the easiest differentiation formula there is, the derivative of e to the x is e to the x. The derivative of e to the x is itself. That is why e to the x is used so often.
So that would f of x, like if e to the x is f of x,
Yes. Every derivative you take of e to the x is e to the x.
but like in this example, would it change the x value?
Yes. Yeah, so example 9, I want you to use this fact to answer example 9. It says if f of x is equal to e to the x minus x, I have find f prime and then find f double prime. So to find the derivative of e to the x, you're using this rule, and then you're finding the derivative of x like we had done before. But I want you to find f prime and f double prime. And then actually, what I might have you do is try example 10. Without me leading you through it at the start, try example 10. It says at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? I just want you to think about that and try it before I go through it. Give you a chance to think about it before I just tell you what to do. So look at examples 9 and 10 right now, and we'll come back and make sure we all understand both.
You're uploading.
Why?
I'm still
We'll discuss
Alright. Just remember anytime you have
Like you need a full. I showed why. Because I don't want, like, with certain rules and you'll never know. You need to know that the derivative.
All right. I think we all got 9. And let's go through 10. At what point on the curve y equals e to the x is the tangent line parallel to y equals 2x? Not at 1. You don't need to guess. What? Yes.
0.69.
Is that the natural log of 2?
Yeah, so I just put 2 in
Oh, because E is the same. Oh, that's where E comes from. Is it the same
Well,
way-
natural log is log base e. Is that what you're asking?
Is E the same defined by E?
Yes. Yeah. All right. Here's how you get the answer for 10 without having to guess or use your graphing calculator to graph it or anything like that. Why are you plugging 2 in for y though? Okay. Yeah, so if the tangent line is going to be parallel to this line, how do you know without seeing a graph, how do you know if lines are parallel? They have the same slope. So parallel lines have the same slope. How do you find the slope of a curve? The derivative. So what is the derivative of e to the x? E to the x. So that means that is the slope at any point is going to be e to the x on that curve. So it would just change with your x value. So the slope at 1 would be e to the first. The slope at 3 would be e to the third. So then what is the slope of this line? 2. So if the tangent line for e to the x has to be parallel to y equals 2x, the slopes have to be the same. So e to the x has to equal 2. How do you solve this for x? Yeah, you can either rewrite this as a logarithmic function or you can take the natural log of both sides to cancel out the e to get then x would equal the natural log of 2. And then, because it says at what point, so natural log of 2 is not a point, that's just an x value. How do you find the y value? Plug it into where?
The equation.
Yes, the function is e to the x. So to find the y value, you plug it into e to the x would be e to the natural log of 2, which is just 2. Because e and natural log cancel. So this would be the point where the tangent line is parallel to y equals 2x, or where the tangent line has a slope of 2. Problem solving. All right, practice is there.
Right into my book.